Hi, my name is Timo Kozak, and together with Vsevolod Archakov and Bogdan Dutchak, we were working on the project BONGA. And we are excited to present you our solution for image stitching taken from drones. Usually, there is a certain territory that has to be captured, and the task is to cover this territory with the photos. Obviously, some territories can be covered with one shot, but this is not the most efficient approach, as it significantly decreases picture quality. So, there is a need to take a couple of pictures from a smaller distance. This leads to the problem of combining all these photos into one big panorama, which allows you to fully explore the desired area in one picture in a good quality. Under work conditions, this solution may be applied to identify the grouping of troops, discover the destruction of the territory, and many other applications that go far beyond martial conditions. To solve the problem of creating a panorama, we decided to approach it in the two main steps. Firstly, we used a mathematical projection to define the corners of every taken image, and then we, using those coordinates, found the position of each pixel in a resulting panorama.
Firstly, we needed to define a mathematical model for our camera, which is taking images from the air. As you can see on the photo, rectangle ABCD is our matrix of the camera, point F is a focus point of the camera. So to find the coordinates of the image on the ground, you need just to pass lines through the corners of our matrix and the focus point. The intersection of these lines with the ground will be resulted coordinates. As our drone rotates during the flight, we need to calculate a transformation matrix for calculating the position of the focus point and all corners of matrix camera. What do we need for this? It's quite easy. We just need to define three matrices which will be responsible for rotation around main axis in R3. The first matrix is a matrix for rotation around x-axis. It corresponds with pitch angle for the drone. The second matrix is a matrix for rotation around y-axis. It corresponds with roll angle. And the last one is a matrix for rotation around z-axis. It corresponds with yaw angle. After we have two transformed coordinates of our focus point and one of the corners of our camera matrix, we need to find a corresponding point on the ground for the line which passes through the corner and focus point. We'll derive this from just basic equation of the line. As we know that our parameter z will be 0, because we consider our ground on 0z, so we can just calculate the parameter d, which will be equal to the last part of the equation, and using this parameter d derive x and y, which will be coordinates for our pixel on the ground.
We collected nearly 100 images from a drone that flew at an approximately 500-meter height. We also processed all their relevant metadata, such as latitude, longitude, and drone rotation angles. And here you can see the quadrangle representation of every taken image on a map.
For building panorama from all our images, the first thing we need to do is to restrict all these images in one quadrangle. As you can see on the image, the black rectangle restricts all our images. As we have areas of all our images, it's quite easy to put corresponding pixel in each image in the resulted panorama. The only thing we need to do just to iterate each image and each pixel, then to identify the geographic coordinate for it, and just put it in the resulted image, which is basically our black rectangle.
So to test our algorithm, we took 4 photos just to reduce the execution time. And as you can see, the final result is a stitched version of those photos with a black frame. And this frame basically represents the fact that we constrained our image to be within those borders by coordinates. As an additional part of our project, we decided to create an image with the best quality, having an intersection area on several images.
In this example, we have two different images where you can see the same crossroad. In order to check the efficiency of the algorithm, we manually blur it. First of all, we have to find key points that correspond to each other. There are plenty of the computer vision algorithms such as orb, sift, surf, and accelerated Kaza. These colorful lines connect corresponding key points. Getting the best key points allows us to compute the transformation matrix and change perspective of one of the images. You can see how common areas overlap after one of the images changed its basis. The next step is applying the Laplace of Gaussian algorithm, which gets rid of noises and takes derivative of the images, in order to evaluate the numerical value of clarity. We split images into small rectangles and choose the clearest one to build a resulting image of them. As a result, we got an image where the crossroad is not blurred.
In the end, we successfully completed our goal for the project. We calculated coordinates of corners for each image and successfully built a panorama using these coordinates. Also, we applied and created an algorithm to improve the quality of images on the overlapping territories. So, thank you for your time watching this presentation. We hope you liked our project.